All right, everyone. Good afternoon. Well, before the lunch break, we discussed this theorem, which gave this necessary and sufficient condition for informativity for quadratic stabilization. And remember that for this theorem, we still needed to assume this rank condition on the state and input data. And also, we were assuming here this particular noise model, namely the norm of W minus is less than or equal to epsilon. So what I already announced before the break is that I want to generalize in two different ways. First of all, I want to generalize the noise model, and secondly, I want to generalize to rank deficient data. So I would just want to drop this assumption that the rank of x minus u minus must be n plus n. So we already did a little bit of the generalization of the noise model. Let me quickly remind you. Right, so before we were assuming that the norm of W minus was less than or equal to epsilon, which was equivalent to this inequality here. And you could reformulate that inequality as the quadratic matrix inequality over here. Now, the matrix that you see here in the middle is, of course, a very specific matrix, depending on this value epsilon, which is the bound on the norm, and we have this minus identity. But what I was proposing before the break is to replace this matrix by some matrix phi of this form. So from now on, we're just going to assume that the noise satisfies this quadratic inequality, where the matrix phi in the middle is given. And we already saw some applications of that noise model, namely energy bounds, norm bounds, the noiseless case, and sample bounds on the noise, and sample covariance bounds. So these are all special cases of this generalized noise model.
The last condition, does it imply that the noise we are considering also in the probability signature?
In principle, you don't have to assume this. So the only thing we are assuming is that the noise satisfies this inequality. But of course, the last bound is the most relevant in the case that you have probabilistic noise. Yeah. But in principle, the only assumption we're making is this inequality on the noise for different choices of phi. Okay, now let's continue. So my question is now, of course, before we had these conditions for informativity for this very specific noise model with the epsilon bound, what changes now if I replace that by this general noise bound? Right? Very natural question. The answer, luckily, not much changes. That's good, huh? So the theorem that holds true is the following. So indeed, we assume now that the noise satisfies this bound. We also assume that phi to 2 is negative definite, and the same rank condition like we had before holds true. So the matrix x minus u minus has full row rank. Under these conditions, the data are informative for quadratic stabilization if and only if there are matrices K and P and a scalar alpha such that P is positive definite and this matrix inequality holds. So if you take a closer look at this matrix inequality, it's exactly the same matrix inequality as we had before. The only thing that changes is this matrix here in the middle. Before we had epsilon squared identity 0, 0 minus I. And simply in this condition now we replace that by the matrix phi. That's the only thing that changes. And you need to assume that phi to 2 is negative definite. So the conclusion is you can also work with this general noise model, and in fact it's not much harder than working with this epsilon bound on the norm of the noise. Right? It's the same, almost the same matrix inequality, just you replace this by a general phi. That's the point. Okay. So that's it for the generalization of the noise model. Now finally, let's also consider this generalization to rank deficient data. For that, I'm going to consider one final theorem from the cookbook. And the theorem says the following. So I will consider again a matrix version of the S-lemma, but the conditions that we have here on n are weaker than we had before. Look at this. So this is the theorem. We assume that n to 2 now is negative semi-definite. Before, if you remember, this matrix S-lemma was always assuming that n to 2 is strictly negative definite. But we dropped that assumption now. Here, it only needs to be negative semi-definite. Means that n to 2 can have some non-trivial kernel, right? So only negative semi-definiteness is assumed. We need a slightly technical assumption, namely that the kernel of n to 2 is contained in the kernel of n to 1. And still the same Schur complement inequality holds as before, with one small change. Namely, because we're no longer assuming that n to 2 is negative definite, it may be the case that n to 2 is singular. Hence, we cannot compute the inverse of n to 2, and therefore I replace now, here, the inverse of n to 2 by the pseudo-inverse of n to 2. So this is denoting the Moore-Penrose pseudo-inverse of the matrix n to 2. So conclusion is here I'm dropping the assumption that n to 2 is negative definite. I'm replacing it by the assumption that it's negative semi-definite. I need this kernel inclusion, and I appropriately change the condition on the Schur complement. Sometimes in the literature, by the way, people call this the generalized Schur complement. It's generalized in the sense that we're not working anymore with the inverse of n to 2, but with the pseudo-inverse. Okay? Great. And then, apart from that, I now also need to assume that m to 2 is negative semi-definite. Let's assume that we have these conditions. Then, the following holds. One quadratic matrix inequality, in terms of the matrix M, holds for all Z real matrices satisfying another quadratic matrix inequality using the matrix N. So this is the same statement as we had before in the matrix S-lemma. If and only if there exist scalars alpha greater or equal to 0 and beta strictly greater than 0, such that this linear matrix inequality holds in alpha and beta. So you see that a difference with respect to the previous matrix S-lemma. Here we need actually two scalars, alpha and beta. Right before, just to remind you, we were always writing m minus alpha n is positive definite. Here we cannot no longer do that. That doesn't work. We need to include a second scalar, beta, which is strictly positive. And then m minus alpha n needs to be larger or equal to this matrix beta I with zeros. So that's a difference with respect to the previous matrix S-lemma. And now you, of course, wonder immediately, yeah, but Henk, why can't I simply work with the same inequality as we had before, right? Why can't I write here m minus alpha n is strictly positive definite? Well, why doesn't that work anymore? So let me attempt to give you some intuition for that. So if you would write m minus alpha n is positive definite here, well, let's have a look what happens then. So remember, always we partition these matrices M and N as, right, M was this M11, M12, M21, and M22. And similar for N. Since this guy we assume now to be positive definite, by the Schur complement lemma, also the 2-2 part of this matrix would be positive definite. Which would imply then that M22 minus alpha N22 is positive definite. Right? By the Schur complement lemma. Okay. Well, we're working in a situation in general here that this N22 is negative semi-definite only. So it may be singular. In the case that N22 is singular, there exists some non-zero vector, let's call it x, such that N22 times x is 0. For some non-zero vector x. Okay. Great. Let's now try to multiply this matrix that we have here on the left by x and x transpose. So what do we get? We get x transpose M22 minus alpha N22 times x. Well, x I chose such that N22x is 0. So the second part here drops. Right? N22 times x is 0. So this would give me then x transpose M22 times x. But M22 is negative semi-definite, so this must be less than or equal to 0. Right? But that cannot happen. Because our assumption here was that this M22 minus alpha N22 is positive definite. So for all vectors x, if I multiply like this, I must get some positive number. Now here I get something non-positive, so I get a contradiction. So in fact, what you can conclude from here is that in this setup that we have over here, if the N22 is singular, this matrix inequality, m minus alpha n greater than 0, is never feasible. There never exists an alpha such that m minus alpha n is positive definite. That's what we showed here. And that's why you cannot work with m minus alpha n is positive definite anymore. Hence, you need these two scalars, alpha and beta, satisfying this inequality over here. Oh. Okay. Good. Now, for the final theorem of today. I would like to apply this now in the context of data-driven control. So instead of applying the previous matrix S lemma, where we assumed that N22 is negative definite, now I apply this more general result. So the theorem that we derived was the following. There are a little bit of small technical assumptions involved, so I will go through them. So you need to assume that phi to 2 is negative semi-definite. This kernel inclusion needs to hold for phi, so the kernel of phi to 2 needs to be included in the kernel of phi to 1. And the Schur complement of phi needs to be positive semi-definite. In fact, also in this context, that Schur complement being positive semi-definite means simply that there exists some noise matrix W minus satisfying this quadratic inequality. Now, so we assume this now on the noise model. And then, it turns out that the data are informative for quadratic stabilization if and only if there exists a matrix K and P and scalars alpha and beta, alpha being non-negative, beta being positive, such that P is a positive definite matrix and this matrix inequality over here is satisfied. So this matrix inequality is a little bit different from what we saw before. Because before we were considering m minus alpha n strictly positive definite. But look, here we applied now this more general matrix S lemma. We have to work with M minus alpha n is greater or equal to this matrix beta I with zeros. So, the matrix here in blue, that's the matrix M that you see here. The matrix in green is matrix N. The alpha is here. This all needs to be greater or equal to beta I with zeros, but here I took the beta term to the left-hand side, and that's why in this upper left corner you have a minus beta I term. Huh? And that's it. That's then the most general result. One thing to note here is that we no longer need this rank condition on the state input data. So we completely got rid of that. You don't need to assume that x minus u minus has full row rank. And in particular, there exist examples in which indeed x minus u minus does not have full row rank, but you can still find this stabilizing controller using this approach. Yeah, that's also in line what Kanat showed you in the noise-free case yesterday, right? Because there also you do not need that x minus u minus has full row rank. What you can show though, just to make one more connection to yesterday's lecture, Kanat showed that in the noise-free case, you necessarily needed that x minus has full row rank, right? Because there needed to exist this right inverse of x minus, such that x plus times this right inverse is sure, right? So necessarily that means that x minus must have full row rank. That's also the case here. So in the noisy case, also necessarily you need to have that x minus has full row rank. But you don't need that the whole block x minus u minus has full row rank. Okay. Now, is that clear, that theorem? Are there any questions about this so far? No? Okay. Ah, yeah, okay, so, but on the other hand, it's satisfied for all the examples of noise models that we had before. Right, because in these examples, for instance, you take phi 1, 2 to be 0, so then automatically this kernel inclusion is satisfied, yeah. Yeah. Yeah, so, okay. There is an intuition when you look at these type of quadratic matrix inequalities. So in general, if you do not put any structure on this matrix phi, it's pretty difficult to assess whether this has a solution at all or not. But if you make the assumptions that phi to 2 is negative semi-definite and this kernel inclusion holds, then you can very easily test whether this is non-empty or not, whether there exists a solution to this inequality. And in fact, in that case, that's equivalent to saying that the Schur complement, or generalized Schur complement, is positive semi-definite. Yeah. Yeah, so it has to do with that. So in general, if you do not put any structure on this phi matrix, it's difficult to work with. But under this phi to 2 negative semi-definite and the kernel inclusion, then you have a theory. On the other hand, I would not say that this is a very strong assumption on phi, because again, all these are examples of phi matrices which satisfy that.
The other two conditions, three conditions that you had written, the other two were like signature conditions. One part we call positive eigenvalues, one part negative eigenvalues.
It is indeed related to signature because of the formula that we had before on the board, where you write this N matrix as the product of three matrices. And then you can relate the eigenvalues of the N matrix to the, or the signature at least of this N matrix to the signature of the Schur complement and the N to 2 block. And that also indeed you can do with the phi matrix. So indeed it's related to the signature. Yeah. Are there any other questions?
Practical implications of that kernel
Yes. This one.
Yeah, so that condition kernel of 522 is a subset of kernel 521.
Mm-hmm.
What is the practical implications of this? And why did you assume this?
Yeah. Well, the honest answer would be, if you assume this, we have a theory. But on the other hand, if you look at, as I was mentioning before, the usual suspects of noise models always satisfy this condition, that the kernel of phi 2 is contained in the kernel of phi 1. So in practice, it's not a very strong assumption to work with, because any sensible noise model that you would work with, like this, satisfies these conditions. And by the way, there are even other noise models that I did not mention here. Suppose, for instance, that the noise is, in addition to satisfying a quadratic inequality, also is contained in a subspace. Right, so W is of the form some matrix E, let's say, times some W bar, where W bar is typically of a lower dimension than W. Also, those type of noise models you can capture using suitable phi matrices. So there are even more examples than the ones that I showed here. But I understand, of course, in these 2 hours I can just give an overview, and it seems to come maybe a little bit out of the blue. But with these examples, I want to stress that really it's not a very strong assumption on phi.
I just wanted, how did you thought of that?
Mm-hmm. Yeah. Yeah, so we wrote this paper on quadratic matrix inequalities, and there it originates. So, as I was saying before, for general matrices phi, already it is not immediate, or it's pretty difficult to understand under which conditions there even exist solutions to such quadratic inequalities. And then you see, once you have these conditions, you have this nice theory. So that's where it comes from. Okay. Other questions? No? Well, I then just want to wrap up and summarize today's lecture. So, what I'll do is present a kind of conceptual algorithm. So imagine that you collect noisy data from some input state system. You have this noise model captured by this matrix phi, and you want to construct this controller from this data. What do you do? Well, again, we consider this model class of noisy input state systems with noise model phi. I collect data. Data consists of samples of the input, u minus, and samples of the state, x. The first thing to do is to check feasibility of this linear matrix inequality. So I check. By the way, you can use different types of software for that. For instance, Sedumi. You check whether this linear matrix inequality has a solution. If that has a solution, then you will get these matrices P, L, and these scalars alpha and beta satisfying this matrix inequality. So there are, at this point, two possibilities, right? Either the solver returns to you, there is no solution, and then you know that the data are not informative for quadratic stabilization, right? Because we have this if and only if condition. So if you do not have a solution to this inequality, you know the data are not informative. But if you find a solution to this inequality, you know the data are informative, and the solver returns to you a matrix P, L, and scalars alpha and beta. What do you do then? Well, you have to compute a control gain K. We do it in a similar way as before. So I define now the feedback gain K to be L times P inverse. And that is a feedback gain that stabilizes all systems consistent with the data. In particular, the true system, which is contained in this set of consistent systems, this controller also stabilizes. That's it. Well, and there may be a few remarks just to compare this to some results in the literature. So one of the appealing aspects is that using this matrix S lemma, today we obtain this necessary and sufficient condition. So it's a non-conservative control design method in the sense that you get this if and only if conditions for quadratic stabilization. Which means that really, if you cannot find a solution to this inequality, if no solution exists, the data are not informative. There are some other LMI conditions in the literature which do not have that property. So even if they don't have a solution, it may be possible to use a different approach to find a controller, right? But that's not the case here. Okay. And something we already discussed before lunch is that the constraint that you have over here is of size 3n plus m by 3n plus m, because P is an m by m matrix. So the constraint here is independent of the time horizon of your experiment. Also, the dimensions of the variables over which you're looking here is independent of t. So P is an m by m matrix, L is an m by n matrix, and alpha and beta are their scalars. So this does not depend on the time horizon of the experiment. Now that can be beneficial if you have a larger data set. Okay, very good. That's actually all I wanted to say today. I again want to thank you very much for your attention. Thank you. Are there any final questions before we start with the tutorials? Yes? Yeah, good question. So no, it turns out that in general there exist multiple solutions indeed. There are multiple solutions, so the solution is not unique. Analogous to the stabilization problem for just a single model, where there are also multiple stabilizing controllers. So in general, indeed, the solution is not unique. Yes? But, well, I would say it is quite clear, because any solution to this inequality, so for any P and L that solve this inequality, you can choose the feedback gain K to be LP inverse. For any solution, you can get this stabilizing feedback gain. So if you just want stabilization, it doesn't matter which solution you pick to this inequality. Any solution will lead to a stabilizing controller.
So, I mean, there are multiple solutions. Are there any ways by which we can...
Yeah, good question. So maybe you would also like to include some performance specifications then, right? We have indeed looked into that. So, for instance, H2 or H infinity performance. And then indeed, okay, the LMI conditions are going to change a little bit because you also need to include these performance guarantees. The controller in particular is going to be stabilizing because there the design specifications are you want to have internal stability and a small H infinity norm from W to your performance output, for instance. So in that sense, that indeed is a way of selecting a specific stabilizing controller, indeed. Yeah, true.
The rate of convergence and all those things can also predict?
Yes, I think you would be able to do that, but I think the Lyapunov inequality then needs to change a little bit. So, okay, I did not do this myself, but if we go back to the Lyapunov inequality, I need to go back very far. Yeah, okay, here. Maybe if you include here a term on the right-hand side, like epsilon I or something, then you can govern the rate of convergence. And I suspect that in that case, again, you can write a linear matrix inequality condition. Yeah.
What about the robustness of this controller? Because you do an experiment under some conditions, you get a control gain K, then you run it on the actual plant, and if the conditions change slightly, ever so slightly, from what the conditions were during the experiment, how robust is this approach?
Yeah, so that's a good question. So here, for the moment, we assume that the true system is time invariant. So these matrices A, S, and BS, they do not change over time. Maybe you can think of ways to keep collecting data in closed loop after you implement a controller. And by using that data, perhaps you could even update the controller online. Yeah. But I have not done that yet. But that could maybe be an approach.
For stabilization, that feedback control that is there. So in general, we need something kind of controllability concepts. So if I just try to connect with previous class lecture, so that stabilizability conditions in the data informativity point of view, it is somehow is playing a role in this when we are designing.
Yeah, so those conditions. Oh, sorry. Those conditions in the previous class you cannot directly apply to this setting because this deals with noisy data, right? But it is true, of course, that your true system needs to be stabilizable for this to work. And in fact, all systems consistent with the data need to be stabilizable. We also looked into conditions under which all of these systems compatible with the noisy data are stabilizable. And again, you can find conditions for that. But like in previous lecture, those are not equivalent. So in the sense that if I have that this whole set of systems, A, B, is stabilizable, that does not mean that there exists a single controller which can stabilize all these systems. And so these two conditions are not the same. Yeah.
Here again, the data is basically we are collecting states.
Yeah.
And the measurements are basically IBS.
True. Yeah, so we have a disturbance that affects your system, indeed. Yeah.
In that case, can we modify this?
Yes, it's possible. In fact, there have been papers on this. So in the case that you have also measurement noise. So imagine, for instance, that instead of measuring the state exactly, you would also have an output equation. Like this. What people have been doing is assuming that also this VT satisfies a quadratic matrix inequality. And then you can again come up with conditions for stabilization of this whole set of systems consistent with the data. So that's indeed possible. And the input-output you also asked about, right? Yeah. So that's actually something Kanat will treat tomorrow. So indeed, here I studied a situation where we measure states. If you work instead of with a state space model with an autoregressive model, so AR model, kernel representation in behavioral theory, you can also come up with conditions using input-output data. Yeah.
So the framework now we have considered, we included the noise vector in the process.
Yes.
Now, let's say if I just, for instance, this x minus, that elements we have got, if I just write it x minus plus delta x,
Yeah, so I think you're referring to this situation, right?
So the same framework will work or?
With some adjustments, yeah, indeed. In fact, you could also think of combinations of both of these. So you have both a disturbance and a measurement noise like this. Yeah.
So the process noise that we're considering here, if you consider a stochastic setting, the most commonly used stochastic model is white Gaussian noise.
Yeah.
And is this applicable to that theorem?
I think one of the approaches, so in fact, one of our colleagues, once wrote a small piece on this. if you have Gaussian process noise, then you can come up with probabilistic guarantees under which your noise satisfies this bound with this sample covariance bound on the noise. So you can have statements like, with a certain high probability, your noise matrix satisfies this bound with this choice of phi's. But that does not mean that you obtain the same guarantees for quadratic stabilization. Because here, really, if we know that this linear matrix inequality is solvable, for sure we can stabilize the true system. But in that setting, yeah, since you only know that with a certain probability your noise is in a set, you lose these kind of absolute guarantees. But you can come up with statements like, with a certain probability, your controller is stabilizing for the true system. No, it's okay.
No, please be there, I will come. So my question is that how do you implement this kind of a control gain K? Because the system A, B is based on past data. And my control will be successful if I can guarantee stabilization in future beyond capital T. So how it is taken care that it will actually stabilize the system in future?
Well, okay. Let me go back a little bit. So this was my control objective, right? So I wanted to find this control gain K such that this is a stable matrix. If this is a stable matrix, then I know for this closed loop system that all my trajectories go to 0. The final LMI condition that I showed ensures that this K is such that this is a stable system. So indeed, as time goes to infinity, the x of t here will converge to 0. Yeah. Also, so you collect some finite data. Based on that finite data, you come up with the controller K. And then you know asymptotically, after that, if you apply the controller, that here your state converges to 0.
Is it because of the assumption of time invariance of the system?
Definitely, yeah, definitely. That's what we use. Yeah, sure. Yeah. Okay. If there are no more questions, I propose we continue now with the tutorial. So we have one exercise for today. It's going to be about today's lecture. And in fact, the tutorial exercise is going to be about a slightly different noise model. So instead of assuming this energy bound on the noise, we're going to assume that each of the noise samples are bounded in norm by epsilon. And that's what the tutorial question is about. So I will now, well, if I can manage with this computer, try to load the tutorial question. Maybe I can get some help for that. And then again, as in the previous days, we'll go around and help and guide you through the exercise. So thanks again.
Let me put it in chat.